Let's continue on to a few more problems in classical mechanics from the part Lagrangian dynamics. So the questions that we are going to discuss in this session have been asked in the previous NET JRF exams. Okay, so we'll try to solve a few of them. So here is the first one. A particle of mass m moves inside a bowl. Okay, if the surface is a bowl like that and there's a particle of mass m moving inside it. If the surface of the bowl is given by the equation z is equal to half a x square plus y square. Right? So this we can call as the constraint. Okay, so the particle is constrained to obey or constrained to be on this particular surface defined by this equation, okay, where a is a constant. The Lagrangian of the particle, you are supposed to find the Lagrangian of the particle. Okay, so this is not a very difficult problem. We can solve it easily. Primarily, the most important thing is that you have to choose the right coordinate system. If you choose the wrong coordinate system, things get complicated. Okay, if you are tempted to use, for example, spherical polar coordinates, you can try and you will see that the thing gets really complicated. Okay, but if you use cylindrical coordinates, you will see that the problem is simpler. All right, especially also by looking at the answer. You see there's an r here, there's a phi, so r, phi, and there's a z here. Right, so it's so we know that the cylindrical coordinates are r, phi, and z. Okay, we can use this as the coordinate system. Right. So what are the transformation equations? Right. So we need the transformation equations as we said earlier. So what are the transformation equations? Let's have a look at this. We'll choose cylindrical coordinates. All right. We'll use cylindrical coordinates. It's known as cylindrical coordinates. So if you are on a surface of a cylinder, okay, and yeah, this distance is called, what do you say? We can call it as r. Okay. It's also this distance. It's the same thing, right? You are supposed to draw it properly. That's the same distance, and this angle is phi, and the height is called as z. Okay, so easily from here you see that x equal to r cos phi, y is equal to r sin phi. Okay, z is z itself. Right, we use z exactly in the same sense as we use it in Cartesian coordinates. All right. So what's the constraint now? Well, let's start writing up the kinetic energy. Okay, T is equal to half m x dot square plus y dot square plus z dot square. Okay, that's how we write the kinetic energy. All right, but we could maybe do it in an easier way. All right, as I said, we could always apply this transformation equation, substitute this, and then solve it. All right, but we know better now. We know that we can write it in this form. You can try this. All right, we can write it in this form. Right, the velocity corresponding to a radial change. All right, the velocity corresponding to a radial change is simply r dot. Okay, and the velocity corresponding to a change in phi. Okay, the velocity corresponding to a change in phi is we can write it as r phi dot. Okay, so this would be r square phi dot square, right? Because when phi changes by a small angle, the distance moved is r d phi, and the corresponding velocity we can write as r phi dot. You can also call this as the angular, okay, the velocity corresponding to the angular momentum phi dot. V is equal to r omega, so V is equal to r phi dot. All right. There's also corresponding to a coordinate z dot. That's z dot square itself. Okay, but we have this equation for z equal to half x square, half a x square plus y square. Okay, it is half a x square plus y square. Right, now you have to, you know, x and y here, so that's equal to half a x square plus y square is r square cos square phi plus r square sin square phi. So that is simply r square. Okay, so it's half a r square. Z is equal to half a r square. Z dot becomes a r r dot. Okay, a r dot. So that z dot square becomes a square r dot square. Right. So this is the kinetic energy becomes the term corresponding to the z dot. Okay, becomes plus a square r dot square. All right. So yeah, that's fine. Okay. Yeah. Now, what about the potential energy? V is equal to, it's mgz. Okay, we can take this as the reference point. We can take origin as the zero gravitational energy point or the reference point. So it's mgz. And what's mgz? Z is equal to half AR square. So it's mg half AR square. Okay, so this is half mg AR square. All right. Now what's the Lagrangian? L equal to T minus V. All right. We have got T here, we have got V here. So we just substitute these things and simplify. All right. So the Lagrangian is T minus V, and that's equal to half m. We can pull this outside. Okay. R dot square plus R square phi dot square plus A square R square R dot square, okay, minus G A R square, okay, minus because we have pulled this half m outside and it's T minus V, so it's minus G A R square. All right. And now we can maybe simplify this a little bit to make it, to match it with one of the options. So we can write this as, we can pull this R dot square outside from here. So that is 1 plus, okay, A square R square and R dot square plus R square phi dot square minus G A R square. All right. So that is the Lagrangian of this system. All right. So you see that we have chosen cylindrical coordinates and things, we get a simple answer. Okay. It's easy to solve it using cylindrical coordinates. All right. Now if you have the time, you try it in spherical polar coordinates and you see that no such simplification is arising. Okay. So we usually choose the generalized coordinates by looking at the symmetry of the system. If it has a cylindrical symmetry, we use cylindrical coordinates, or if you have spherical symmetry, you use spherical coordinates, etc. Right. So this is the answer. Which option is that? Which option is that? I think this is it. Okay. 1 plus A square R dot square plus R square phi dot square minus G A R square. Right. So option D is the correct answer. This question was asked for one of the NET exams. You see, it's easy to solve these questions if you know what you are doing. Okay. With a little bit practice, you can solve any problems appearing from this section. Okay. This is not extremely complicated. It's an easy problem. And problems have been asked, okay, using a system of springs, right? There are springs connected to pulleys, or spring connected with masses, or a number of springs connected, okay, and displacement in a horizontal plane or vertical plane, etc. Right? Such questions can be asked. So one such question was asked for NET JRF December 2012. Let's try to solve this. Okay. So 3 particles of mass m are connected by 2 identical massless springs of spring constant k. Right? They both have the same spring constant k as shown in the figure. Okay. If x1, x2, x3 denote the horizontal displacement of the masses, okay, from their respective equilibrium positions. So x1, x2 and x3 are the displacements from the equilibrium positions. Right? Now you are asked to find the potential energy. Okay, you are asked to find the potential energy of the system. Right? You can also write down the Lagrangian, but now we are asked the potential energy. It's just part of that problem. Okay, so we can do this. All right. So let's look at, in order to find the potential energy of a spring, I think I have mentioned this before. In order to find the potential energy in this case, all right, you need to know the extension of the spring. Extension of the spring means how much the spring extends from the equilibrium positions. Okay, this needs to be known. Okay. In this case, how do we write the extension of the springs? Okay, so if you look at the spring 1, the extension of spring 1 from equilibrium position can be written as x2 minus x1. All right, this is the important thing that you need to identify here. Once you identify this, the problem is done. All right, here the important thing, the important point where your mind has to be applied is to find the extension of the spring. All right, the equilibrium position of this is given by x2, of this one it's x1. Okay, so x2 minus x1 would be the extension of the spring from the equilibrium position. You can check this. All right, you can just check, you can just look at this. Okay, so if x1 is in the opposite direction, all right, x1 is in the negative x direction, then this becomes plus. All right, and the extension increases and the potential energy will increase. All right. So if x1 is in this direction, if the displacement is in this direction, and let's say x2 is the displacement from the mean position of particle 2 of mass 2 of this mass. All right. Okay. So if x1 is in this direction, then we see that the potential energy decreases, right? Because whatever extension is caused by x2 is compromised by this x1. All right. It brings it together. Right. So x2 minus x1 is the correct thing. Similarly, the extension of this spring would be x3 minus x2. Okay, that's it. We have solved the problem. Once we know the extension of the spring, we know the potential energy is half k x square, where x is the extension. Am I right? I hope this is clear. You can check this. Okay. It makes sense to write it like this. All right. Okay. Now, if that's clear, we just have to write the potential energy V is equal to half k x2 minus x1 square plus half k x3 minus x2 square. That's it. Right? It's a matter of simplifying this. So let's write it down. Half k, since it's common, we can pull it outside. X2 square plus x1 square minus 2x1 or 2x1 x2, all right, plus x3 square plus x2 square minus 2 x3 x2. Okay. Now we can also simplify it further. Okay. X1 square appears only once, so we write it there. X2 square appears twice, so it's 2x2 square. All right. And from here you can pull out this 2x2 because x2 is there. All right. So let's pull out minus 2x2 to match it with the one of the options, and you get minus 2x2. You have got a plus x1 there and a plus x3 over there. Okay. And we also have this x3 square plus x3 square. Okay, is that it? X1 square plus 2x2 square plus x3 square minus 2x2 x1 plus x3. Okay, which option is that? See, x1 square 2x2 square. No, that's not correct. X1 square plus 2x2 square plus x3 square minus 2x2 x1 plus x3. So this is the correct answer. Okay, option C. Option C. Okay. So as you might have noticed here, when you have a spring, when you have a problem involving a spring, the thing you have to identify is how to obtain the extension of the spring. All right. In some problem it doesn't matter. In the case of linear oscillator, for example, it doesn't really matter because that constant part will disappear. All right. But in such cases as these, we have to be careful. Right. We'll do more problems using different systems constructed using springs, masses, pulleys, etc. Okay. All right, here's another problem. It's a simple problem, but here we are asked to find the solution to solve the Lagrange's equation. We have to write the Lagrange's equation, which is a differential equation obeyed by the system. All right, and we have to solve it. And here, the Lagrangian of a particle of mass m moving in one dimension is given by L equal to half mx dot square minus bx, right, where b is a positive constant. The coordinate of the particle x of t at time t is given by, right, in the following C1 and C2 are constants. So we have to write down the Lagrange's equation and then solve it. All right. So this is a simple problem, and we see how these things are done. Okay, what it exactly means. So let's do it. We have got L equal to half mx dot square minus half mx dot square minus bx. Now let's write down the equations of motion. All right, that's a different. We have just one coordinate here, so we'll get an equation governing the time evolution of this coordinate x. Right, that's what we'll get. So dou L by dou x dot is mx dot. Okay, d by dt of dou L by dou x dot is equal to mx double dot. Okay, all right. So it's mx double dot, and here you have dou L by dou x is equal to minus b. So what's our equation of motion? It's simply mx double dot is equal to minus b. Okay, that's our equation of motion. Now you see this is a second order differential equation for x. Okay, we just solve it. Right, we just solve it and obtain. So first maybe we can write this in this form. This can be written as m dv by dt. Okay, m dv by dt equal to minus b. Okay, because x double dot is the acceleration. X double dot is d by dt of x dot, and x dot I have written as v here. All right. So here first we solve for, first we integrate this. We see that m dv is equal to minus b dt. You integrate on both sides. Okay, and you see that mv is equal to minus bt, right, and plus there's the constant of integration, we'll take it as c1, right, plus there's a constant of integration, we'll take it as c1, right, because it's an indefinite integral. Now we see this v. What is v? v is again dx by dt. So this equation means m dx by dt. Since it's a second order differential equation, we have to integrate it twice. Okay, m dx by dt is equal to minus bt plus c1 or dx. Okay, we are supposed to find x of t. All right. So you see that dx equal to minus b by m t dt plus c1 dt. Right, now you integrate on both sides. You integrate on both sides. You see that what we have here is dx equal to integral dx equal to integral minus b by m dt, okay, plus integral c1 dt. Okay, this is what we have. Right. Now when we integrate this, there will also be a second constant of integration which we will call c2. Okay. So you see that x is equal to minus b by m, sorry, there's a t here, so it's minus b by m t dt, okay, minus b by m, it's a constant, and this becomes t square by 2, okay, plus this becomes c1 t, and here I've got c2, or we say x of t. You've got x as a function of t. This is what we mean by solving an equation of motion. All right, you get the time evolution given any t, you know where the position is, okay, what x would be given any t. All right, so this is minus b by 2 m t square plus c1 t plus c2. That's it. Right, that's c1 and c2 are constants of integration. So this is what the Lagrange's equation actually does for you. It tells you the time evolution of the system, or how the configuration of the system changes with time. Right? It's an equation governing the time evolution of the system given the initial conditions. Okay, here c1 and ct are two initial conditions. Given the initial conditions, you can find the configuration of the system at any later time or at any earlier time. Right? That's what the Lagrange's equation allows us to do. Now, all the problems may not have such a simple solution, but in principle we can solve it and find the configuration of the system as a function of time. All right, here we just have one coordinate. In the case where we have a number of coordinates, you will get qi of t. All right, this would be the solution of the equation of motion. All right, you will get how each of the coordinates behaves. You will get an expression for q1 of t, q2 of t, q3 of t, etc. All right, so this means that given the initial configuration in terms of these initial conditions, that's what we call as initial conditions. Given the initial configuration or given the initial conditions, all right, what's the initial configuration and what's the velocity, initial velocity, okay, you can solve this problem by simply integrating the Lagrange's equation. Okay, all right. So that brings us to the last problem that we are going to discuss in this session, right? So here we have got a particle that moves in a potential v is equal to x square plus y square plus z square divided by 2. Okay, which option was that? I forgot to mention the option. Which option was that? It is this. It's option A. All right, it is option A. All right, so you see that once you get the concept, it's quite easy to solve most of the problems that are being asked. Some problems needs a bit more deliberation. We'll do such problems also. Okay, so here this is another simple problem. Once you know the concept, all right. So earlier I had explained to you that this equation means, all right, d by dt of dou L by dou qi dot minus dou L by dou qi is equal to 0. Okay, this means that if some of the coordinates, suppose the qjth coordinate, all right, the jth coordinate does not appear in the Lagrangian, then this term corresponding to it becomes 0. All right, suppose there's a word for it. We said that it's called as cyclic. Okay, qj is cyclic. One of the coordinates is cyclic. Then we immediately get a conservation law. Okay, dou L by dou qj dot is equal to 0. Right, and this dou L by dou qj dot we call as the momentum. It's the momentum conjugate to qj. Okay, this is what we call as the momentum conjugate to qj. Okay. All right, that's the momentum conjugate to qj. We can call it as pj. Okay, pj is equal to dou L by dou qj dot. Right. Now, as we said, if this qj, coordinate that you are talking about is an angle, then the corresponding conjugate momentum is an angular momentum. Alright. So this is, as I said, a special theory of a special case of what we will later call as, what we will later see in more detail perhaps. Okay, it's a special case of what's known as the Noether theorem. Right, Noether theorem. German mathematician. Noether's theorem. Okay. Emmy Noether. It's named after Emmy Noether. Brilliant mathematician, genius. Okay. So here we have got a particle. This is the idea that we'll be using to solve this problem. We know the idea of cyclic coordinate, and we know that if a coordinate is cyclic, the corresponding conjugate momentum is conserved. Okay. So here we have got a particle that's moving in a potential given by this equation, right? Which component of the angular momentum is or are constants of motion, right? This is what we need to find. Okay. So this can be done easily by identifying a cyclic coordinate. Okay. If there is a cyclic coordinate, then the corresponding momentum will be a constant. Right. So since we are talking about rotation, and this is called rotational symmetry. Right. If an angular momentum is conserved, angular momentum about an axis is conserved, we say that there is a rotational symmetry about that axis. Right. So for example, if theta does not appear, okay, or let's say phi, for example, if phi does not appear in the Lagrangian, that means that the Lagrangian does not change when you change this phi, right? So there's a rotational symmetry. It doesn't matter whether the system is here, it doesn't matter whether the system is here, it is exactly the same, all right? It has exactly the same Lagrangian. The system does not change, or it has exactly the same equations, okay? All right, so then we say that there is a spherical symmetry. So if the angular momentum is conserved, or if there's a spherical symmetry, if there's a rotational symmetry, then angular momentum is conserved. Okay. So we can use spherical polar coordinates here. Let's use spherical polar coordinates. Okay. Spherical polar coordinates. Okay. All right. So I'll give a rough sketch of it in case you have forgotten these things. All right. So you have got some object there of mass m, and then this distance to that object from the origin is called r. This angle from the z-axis is called theta. We'll call it like this. Okay. And if we can project this onto the xy plane, we can project this onto xy plane. Okay. This is 90 degree. This is supposed to be 90 degree. I hope it's clear. All right. Now this angle is phi. This angle is phi. All right. And this length here, you can see that it is r sine theta. Okay, this length is r sine theta. This is r. Right. Okay, so with that we can write down the transformation equations easily. You may already remember that x is equal to this line. This length is r sine theta. So x equal to r sine theta cos phi. Okay, r sine theta cos phi. Y is equal to r sine theta sine phi, okay, and z is equal to r cos theta. Z is equal to r cos theta. Okay. So what's the potential here? The potential energy they have given is V is equal to x square plus y square plus z square divided by 2. Okay, x square plus y square plus z square divided by 2. All right. Now if you substitute all these things, you see this becomes r square sine square theta plus r square sine square theta cos square phi plus r square sine square theta sine square phi plus 1 by 2 r square cos square theta. Okay, 1 by 2 r square cos square theta. Now this simplifies to, we have got cos square phi plus sine square phi is 1, so you get r square sine square theta from here. Okay, plus half r square cos square theta. You can simplify it further if you want. You can go one more step and write it, maybe write cos square theta as the 1 minus sine square theta, and then you can write it in terms of sine square theta. But we don't need that immediately because we have to identify the cyclic coordinate. Right? So we see here that phi does not appear in the potential, but theta does. Okay, phi does not appear in the potential, but theta does. R also appears. So when you change R, the Lagrangian will change. When you change theta, the Lagrangian will change. But when you change phi, the Lagrangian does not change. Okay, when you change phi, the Lagrangian does not change. All right, you can also look at the kinetic energy. Okay, T is equal to half m. Right. So the velocity this velocity corresponding to phi dot is r sine theta phi dot. Okay, so that is okay. For corresponding to r, it's r dot square. So it's r square sine square theta phi dot square. Okay, plus we also have r square theta dot square. Okay, so that's kinetic energy. Right. So you see that also in the kinetic energy, phi does not appear. Phi does not appear. All right. So we can say that phi does not appear in the Lagrangian. Phi does not appear in the Lagrangian. That means that changing phi, all right, or rotating, changing phi is a symmetry of the system. Changing phi changing phi is a symmetry transformation, right, or a symmetry transformation of the system. Or there's a rotational symmetry. In other words, there's a rotational symmetry about the z-axis. All right, if you change phi, the system does not change. You can say there's a rotational symmetry about the z-axis. If you rotate the system about the z-axis, the Lagrangian does not change. So the corresponding angular momentum is conserved. We can say it's p phi. Okay, and what's p phi? P phi is the angular momentum corresponding to a change in phi, or corresponding to, let's say, velocity phi dot. Okay, you see that the direction of phi dot, you know how to obtain the angular momentum. The direction of phi dot is along the z direction. You use the right hand rule. All right, the direction of phi dot is along the z direction. So the direction of p phi is also along the z direction. Right, the direction of p phi is also along the z direction. So we can say that Lz is the conserved quantity. Lz is the conserved quantity. All right. What about Lx and Ly? Okay, is there a symmetry if you rotate about the y-axis? Is there a symmetry when you rotate about the y-axis? So you see that when you rotate the system, or if you take the system around the y-axis, theta changes. Okay, when theta changes, Lagrangian changes. So if you take the system around the x-axis, right, if you take the system around the x-axis, also theta changes, and there's no symmetry. All right, so there's only one symmetry, that's if you take the system around the z-axis. All right. So if there's a symmetry around y-axis, Ly would be conserved. If there's a symmetry around x-axis, all right, if you take the system around x-axis, Lx would be conserved. All right, that's not the case because theta appears here. All right, so we see that only Lz is conserved. Only Lz is conserved. All right, later on we'll see this concept of generator. We'll say that Lz is the generator of rotation about z-axis, and Ly is the generator of rotation about y-axis, etc. All right. So generator is the conserved quantity, but we'll see that later. We'll see the concept of generator later on. All right. So we see that the trick here is done by this z square by 2. Z square by 2. This is what brings the angular dependence. Okay. This is what brings the angular dependence. Okay. All right. Because the potential, this term makes the potential depend on theta. Okay. All right. So I think it's we'll keep the lectures short. I think it's time to wind up now. So we have done 4 problems, all from the previous NET question papers, asked from the first module using the Lagrangian formulation and cyclic coordinate and symmetry properties. Okay.